Thanks, man. Hello. Yeah, good morning from Australia. Good afternoon to everyone across the other side of the world. We are Geo-Adelaide, and it's Zulfikar, Yudho, myself, Ben, and An, and we are based out of the University of Adelaide in the School of Civil, Environmental, Mining, Engineering. And so Yudho, unfortunately, is back in Indonesia, so he can't present with us, but this is how it's going to roll. Myself, I'll be introducing it, the problem, the parameters that we've got, and the assumptions, and then going to methodology. Zulfikar will be going analysis, design procedures, deterministic and probabilistic analysis. And then 2 at the end is the final design selection, construction, risk analysis, and mitigation and conclusion. So every year, thousands of kilometers or miles of underground excavations are undertaken across many disciplines, mining, civil. This is expected to continue with the trends. And with this demand increase, we need to understand really what goes into this international multidisciplined engineering feat. So there's just a lot of cogs into one system. So this is our problem definition. As illustrated, we've been tasked with exploring a 3-meter radius tunnel excavated at least 60 meters below ground level, although we were able to put it deeper. The material is represented by Moore-Klom failure criteria with 2 faults present, with scenario 1 having just the upper fault, and scenario 2 brings in a lower fault. The upper fault acts as an impermeable barrier to fully saturated material above it, the 56-meter zone. The boundary stress conditions are 1.56 in plane principle, minor in plane is 0.96, and out of plane is 0.624. The vertical stress is purely overburden, and the stress is uniformly distributed around the tunnel. Built into the model, we have assumed the rock mass to be isotropic and infinite, with water in a steady state. An elastic plastic and Moore-Klom shear criteria for the block and joints respectively to illustrate the effect of a plane and the elastic stress near the openings. These displayed values that you can see are the assumptions and given values. From the given values of the brief, we match the strength profiles to the closest unit, and then we use these properties as the assumed. So we match the unit from the given and then use the assumed from that unit, which is sandstone. All these properties are assumed to be statistically independent for the modeling. So this is where like the fun really begins. We start investigating this scenario. With the model set up, we use deterministic and probabilistic methods to explore the variables, issues, and variations that we all know and appreciate can occur on engineering designs. So why probabilistic analysis? Well, one of the main problems and challenges within geotech is balancing and compiling a full domain picture of the environment versus what really is practical. So we'd love to drill 1,000 drill holes in an area to capture the full extent, the variations and the localized ground conditions, but really that's not economical or practical. So we have to build in these variables into our models. As shown, we have a coefficient of variation up to 0.3. These large values, as will be illustrated later on, they cannot be ignored due to the potential variance. To account for this variance, we use probabilistic analysis. This illustration shows quite nicely how a coefficient of variance can affect the safety. We recorded the probability of failure as this area under the curve, which was the number of simulations with a factor of safety less than 1 against the total run simulations. If you look across to the graph, you can see model B starts out with a mean factor of safety of 1.7 higher than model A, but due to the coefficient of variance of 0.3, it actually fails more times than model A. So by using a deterministic analysis, you'd be using the 1.7 value and assume that it's fine, but by using probabilistic analysis, you'd probably model A shows that it's actually the better option. This also displays the importance of counting in this variance and the full behavioral possibilities at the extremes. You see, deterministically gives you one scenario which could be safe, but then you look to the right, and the probabilistic analysis actually shows that it can experience severe deformation. To model all of this, a 2D plane strain finite element model from Rock Science 2 was used, using deterministic and probabilistic methods. The plane strain analysis with Gaussian elimination solver was used. 500 iterations with a 0.001 tolerance and graded meshing with a 6-noded triangle element. There was stage simulation in Kirk's solution and gravity-based fail stress with more Coulomb failure and slip criteria. We also located the center, the tunnel in the center of our model, and used 8 times radius away from the external boundaries, which have fixed conditions, to reduce the likelihood of boundary influence. So I'll now hand over to Zulfikar.
Thank you, Ben. I'm Zulfikar Ali, and I'll be covering the deterministic and probabilistic analysis. Now, we performed an elastoplastic analysis of the tunnel using the mean values of the rock mass in order to find the effect of the fault on the stress distribution around the tunnel and the probability of the slip. Now, according to Brady and Brown, if angle of friction of a fault exceeds 24 degrees, no slip is predicted on the plane. For this specific model, we observed that the critical angle of the slip is 2 standard deviation below the mean, that is 20 degrees. So above 20 degrees, it was safe. Below 20 degrees, there were a lot of yielded elements. As expected, there is a sharp drop of the normal stress where the joint passes over the excavation. The maximum normal stress was found to be 1.05 MPa, maximum displacement of 4 millimeters. Likewise, a reversal of the shear stress direction over the excavation was observed, suggesting a slip which produces an inward displacement of the rock on the underside of the plane of weakness. Now, the maximum shear stress was found as 0.4 MPa and a shear displacement of 1.5 millimeters. Now, for the tunnel support design, it's important to know the total deformation in the radius of the plastic zone. When a tunnel is excavated, there's a certain amount of deformation, usually which ranges between 35 to 45% of final tunnel wall deformation before the tunnel support should be installed. Now, for this purpose, we performed a stage excavation using an internal pressure reduction method in 11 stages by reducing the internal support pressure in increments of 10%. The final stage with the 0 internal pressure was used to determine the amount of final deformation prior to the support installation. The maximum displacement was found as 42 millimeters and the radius of plastic zone was 7.915 meters. Now, to compute the tunnel deformation at point of support installation, the empirical relation developed below this and dead reaches were used. Now, for the measured displacement and the radius of the plastic zone, using the plot generated by Velocopoulos and dead ridge, the maximum amount of pressure prior to support installation was found as 19 millimeter, which corresponds to a 20% of internal support pressure. Now, for the design of the support pressure, we modeled a 3-stage simulation. And during the excavation stage, the 20% of the support pressure was applied, and in the last stage, the tunnel liners were applied. The detailed support design and its analysis would be discussed in the later part of the presentation. Now, one of the governing factors in this problem was that the groundwater table was right on the surface and the fault was acting as an impermeable layer. So the fault slip may allow the groundwater to seep into the tunnel until a steady state is achieved. In order to observe this, a drawdown analysis of the water table was performed using a coupled analysis. As can be observed that the drawdown of water table due to the drain boundary around the tunnel and the flow lines showing the direction of the flow of water of the excavation is met. The liners successfully accommodated the load without any further failure. Lastly, the second fault was added to analyze its effect on the stress distribution in the plastic zone. It was found that both the tunnel displacement and yield elements were affected by the addition of this extra fault. An increase in the normal and shear stresses can be observed, resulting in a higher probability of slip and larger formation around the tunnel boundaries. Now, for the probabilistic analysis, as we discussed earlier, that due to the large uncertainties in the rock mass parameters, it was imperative to apply the statistical methods. Now, in RS2, the probabilistic analysis follows the following step. We first assign the probability distribution to the properties, then generate samples for each parameters. We calculate the strength factor for each simulation, and at the end, the probability of failure is calculated. For this model, we assume normal distribution of the strength parameters, and a 3 sigma rule was applied to select the upper and lower bounds. The RS2 provides 3 sampling methods, with point estimate being the simplest, and Monte Carlo and Hyper-Latin more detailed. We utilize both point estimate method and the Monte Carlo simulation. First, a sensitivity analysis was performed by running a probabilistic analysis of each single parameter. A combined probabilistic analysis was run incorporating all the strength parameters, including the fault parameters. As can be observed, cohesion was found as the most sensitive parameter, but the tensile strength of the rock mass was found amongst the least. Following the sensitivity analysis, to find the optimum depth of the tunnel, analyses were performed for tunnel depth between 60 and 75 meters at an interval of 5 meters. Normal and shear stress distribution and displacement corresponding to these depths are as shown. The maximum stress and deformation corresponding to the depths are shown on the left, while the probability of slip at various depths for a single fault and a double fault scenario are shown on the right. Based on the analysis, a safe depth of 65 meters was recommended for single fault, while a depth of 75 meters is recommended for the 2 fault scenario. Now for the next part, I would hand it over to Elvis.
Thank you, Ali, for showing us the analysis. So in the next 5 minutes, I will be talking about the design, construction, and risk mitigation methods. Yeah. Can I have a control, please? Yeah.
Yeah, okay.
Yeah, I'm good. Yeah. So just a quick sum up. So based on the probabilistic analysis, the safe tunnel depth was found to be 65 meters for single fault and 75 meters for 2 faults, achieving the desired requirement for the probability of fault slips less than 5% and the factor of safety of 1.5. Next, the tunnel support design was finalized. We found that a composite tunnel liner of concrete reinforced with 6 millimeter diameter wire mesh is safe to support the tunnel deformation. The concrete and reinforcement properties used are default values saved in the software and showed in the slides. To analyze the design, support capacity diagrams were generated in axial force versus the moment space, and also in axial force versus the shear force space. The support capacity diagrams are used to determine the factor of safety of the tunnel liner. All the values of acting forces and moment are shown in the black data points. It can be seen that all the data points fall within the 1.5 meters factor of safety envelope, which is suggesting no further changes are required. In terms of the construction method selection, generally there are 2 main methods, which are drill and blast and tunnel boring machine. So to decide which method should be used, we analyze the benefits of each method and select the one that fits better into our design requirements. Length of the tunnel is one of the most critical factors to consider. Drill and blast will benefit shorter tunnel due to less startup time. while TBM is more favorable for longer tunnel due to higher excavation rate and extra cost in boring bit replacement. And Trim Plus can create more flexible space to install the waterproofing layers and suitable for irregular tunnel shapes, while TBMs is more suitable for circular tunnel with larger diameter, which is our case here. So, and when it comes to unexpected and varying rock mass in hydrogeological conditions, Trim Plus will do better for unexpected conditions. And for TBM, it will be more efficient if the rock mass conditions is good enough and foreseen. And other non-geotechnical aspects such as labor access and environmental aspects also can be selection criteria. Tunnel boring machine may require mechanics for operation, while Trim Blast will require specific skill labor. And also the impact on the surrounding rock and environment is less in tunnel boring machine, which make this a more favorable method. So in conclusion, tunnel boring machine is selected due to competitive advantages in geotechnical, hydrogeological, tunnel circular cross-section, and environmental impacts. There are also certain risks in tunnel construction, and
So you
in
just to clarify, you guys have half a minute left.
Yes, in this numerical analysis. So firstly, we wrong estimate the stress. Yes, and to mitigate that, we need to properly monitor the soil behaviors and update the data to mitigate this risk. Okay, and oh, sorry, cannot go back. Yeah, and some other risk is we need to introduce is the under break and over break during the blasting, and we need to monitor the process to minimize this risk. And we also need to pay attention to the inhomogeneity of the fault, and we need to further investigate it into it and give the ground support method. And excessive water pressure can also be a critical risk, and we need to do prevention from the surface and also from underground by enhancing the drainage and monitor the water inflow. So to conclude, the deterministic and probabilistic analysis were performed for a circular excavation with two scenarios, one fault and two fault, and we found that it is safe for one fault at 65 meters below the ground, and when two faults present, it will be 75 meters. And the referred excavation method would be tunnel boring machine, which will help us reduce the impacts on the surrounding environment, and is better controlled in the variance of mechanical ground conditions. Okay, so that's the end of our presentation. So thank you so much for your attention. If you have any questions, please do let us know. Thank you.
Great. Thank you, team Geo-Adelaide. I just want to note that you guys took 16.5 minutes. So judges, please consider that while you are scoring for the time. And then I will leave it up to the judges.
Yeah, so one question to begin with, is a tunnel lining necessary?
Obviously, for the support, yes, I think, because in our case, we are considering the groundwater table. So one of the major risks that were involved was the water inrush. So for that purpose, a completely sort of an insulated, we must have a proper tunnel lining system that should not allow the water to inrush.
And what's the mechanism for the water to get to the tunnel? What changes?
So because of the water inrush, there could be a lot of displacement. The displacement would be increased and a lot of subsidence on the ground. And it can also generate a lot of excess pore water pressure that needs to be incorporated in the tunnel analysis and final design, I think. So in our case, specifically, if we talk, so because the fault above the tunnel, it was acting as an impermeable layer. So the moment there would be a fault slip, there's a likelihood that the water would flow down and it would create extra pore water pressure and also generate risk into mud inrush or the flood in water inrush. So.
Do you think your choice of permeability would make any difference?
Obviously. So if the now because the lithology is same here, we do not have much information about the same. But if the permeability is higher in the upper layer and it's lower in the bottom layer, there would be much more penetration of the water, and it's vice versa. It's opposite. If the layer in the tunnel is made completely impermeable, I think so that there would be no effect on that.
Thank you.
I have a follow-up. How does this all relate to your thrust and shear design of your liner?
Sorry, if you could repeat the question. What relates to design of
This
liner?
is a follow-up. How does this all relate to your thrust and shear diagram for your liner?
Okay, but we basically all this the thrust and the shear diagram was based on the idealized situation that we created. So we just wanted to check the amount of diffusion that is occurring because of the saturated layer and under the unsaturated dry condition, and if the liner that we are providing is sufficient enough to hold that factor of safety limit for us. So the design of the liner and then further analysis was based on the same.
Okay.
I'm good. I have no question.
Yeah.
Okay. So I guess thank you, Geo-Adelaide, for a wonderful presentation.